Welcome to the fifth session of chapter number 11, heat, and the subtopics are heat capacity, specific heat capacity, molar heat capacity, second law of thermodynamics, Carnot engine, entropy. Heat capacity. Heat capacity is defined as the quantity of heat required to raise the temperature of a body by a unit degree, and its unit is joule per Kelvin. Specific heat capacity is the quantity of heat required to raise the temperature of a unit mass of a substance through unit degree of a temperature, and the SI unit is joule per kg. To clear its concept, have a look on a video.
In this video, we're going to learn about heat capacity and specific heat. First, we're going to learn what those terms mean, and then we're going to learn an equation that we can use to calculate specific heat. And then finally, we're going to use that equation to solve the problem. Now, as an object gains heat, it gets hotter. This is a relationship that isn't exactly anything new or profound. And you've probably experienced this relationship firsthand when you tried to eat something or drink something that was really hot and burn your tongue. Now, different types of objects do not heat up in the same way. We can supply the same amount of heat to metal and plastic, and the increase in temperature they experience is going to be different. Here's an experiment you can try at home. Take some water and get it up to boiling. And then once it reaches boiling, you could put two types of spoons in there. You can take a metal spoon and then also take a plastic spoon and place those into the boiling water and let them sit there for about 3 to 5 minutes. Now be careful because there is boiling water and these spoons, well, one of them is going to get pretty hot if you touch it. After 3 to 5 minutes, go ahead and touch the plastic spoon. And be really, really careful as you touch that plastic spoon because the steam coming off is going to be pretty hot. Now, it should be pretty easy to touch and it should almost be at room temperature. Now grab onto the metal spoon and you'll notice that it gets extremely hot. This is why we like to stir and cook with plastic utensils or wooden utensils because they don't heat up as easily. Now, the reason the metal spoon heated up a lot quicker than the plastic spoon is because of something called heat capacity. Now, heat capacity is the amount of heat required to increase the temperature of an object by 1 degree Celsius. And our experiment proved that metals need less energy than plastics in order to raise their temperature. And so the heat capacity of the metal would be lower than the heat capacity of the plastic. Now, specific heat is short for the specific heat capacity. And this is the amount of heat required to raise the temperature of exactly 1 gram of a substance by 1 degree. And we usually measure heat in units of joules. And here's the equation we use to calculate specific heat. We use the symbol C, capital C, to represent specific heat. And we take the heat, represented by this lowercase q, divided by the mass of the substance times this change in temperature. This symbol right here, delta, means change in, and the T is representing temperature. So heat is measured in units of joules, and mass is measured in units of grams. And temperature is measured in units of degrees Celsius. The units for specific heat end up being joules per gram degree Celsius. So all of this is included as the unit for C. So when we calculate C, this is what we would put next to our answer. So let's try using this equation to solve a problem. So here's the problem that we're going to solve. It says an empty aluminum can has a mass of 12.3 grams, and the can is heated from room temperature of 25 degrees Celsius up to 48.4 degrees Celsius. It says how many joules of heat was required to raise the temperature of the can given the specific heat for aluminum is 0.90 joules per gram degree Celsius. When I solve word problems like this, I like to underline the given information in green and then what the question is asking me to solve for in red. The next thing I like to do is just write the equation I would use to solve the problem. Since I'm working with specific heat, I'm going to write down the equation I just learned. And then I'll think about what pieces of information I have. I know the specific heat, that's C. And then I also know the mass here, it's 12.8 grams. So this part and this part. I also know the change in temperature. It went from 25 degrees Celsius to 48.4 degrees Celsius. To calculate the change, whenever we see the delta, we always take the final and minus the initial. So I have 48.4 degrees minus 25 degrees, and I get a change of 23.4 degrees Celsius. And so I'm going to be solving for this value right here, this Q. That represents the joules of heat. So I'm going to rearrange this equation by multiplying both sides by mass times delta T. That's going to move it over to this side and cancel it on this side. And now it's just a matter of plugging everything in that I have listed over on this side. So I can plug this into my calculator, 0.9 times 12.8 times 23.4, and I get a heat of 270 joules.
Molar heat capacity. The amount of heat required to raise the temperature of 1 mole of a substance by 1 Kelvin is called its molar heat capacity. SI unit of molar heat capacity is joule per mole per Kelvin. We have two types of molar specific heats. One is at constant volume and other one is constant pressure. So the quantity of heat required to raise the temperature of 1 mole of a gas through 1 Kelvin at constant volume, it can be represented as CV. On the other hand, the quantity of heat required to raise the temperature of 1 mole of a gas to 1 Kelvin at constant pressure, it is denoted by Cp. So Cv denotes heat molar specific heat at constant volume, and Cp represents molar specific heat at constant pressure. In this derivation, we have to prove that Cp minus Cv equal to R, molar specific heat at constant pressure minus molar specific heat at constant volume equal to the gas constant. To prove it, let's consider a system that comprises n number of molecules of a monoatomic gas in a cylinder provided with a movable pistons. Assumptions. We have to take some assumptions. The system contains an ideal gas. The piston is frictionless. The expansion is reversible. Both Cp and Cv are constant for the temperature change. Consider two isotherms of an ideal gas. Two isotherms you can easily see in the graph, PV graph. On the x-axis there is a volume and on the y-axis there is a pressure, and we have two isotherms, two curves, two isotherms here. Consider two isotherms of an ideal gas which are differing in temperature by delta T. If the piston is fixed and the gas is heated, the path AB is a constant volume process. You can easily see here AB. This path, this straight line shows AB, and this path is a constant volume. You can easily see that there is a no change of volume in path A and from path A to path B. So this path is for the constant volume process. In this case, the heat absorbed at constant volume is, this is the formula of molar specific heat at constant volume. QV equal to NCV delta T. Since del V is equals to 0 because the volume is constant, that's why delta V equals to 0. Hence, applying the first law of thermodynamics. First law of thermodynamics is delta Q equal to delta U plus delta W. But we know that delta W is 0 in this case, so it becomes delta Q is equals to delta U. By comparing equation 1 and 2, we can compare equation 1 and 2 because one side of both the equation is same. So it becomes delta U is equals to NCV delta T. Now let the gas be heated through a reservoir when it is allowed to expand, keeping the pressure constant along the path AC. In this path, pressure is constant. There is no change in the pressure. Then heat absorbed is delta Q is equals to NCP delta T as the piston moves up a distance delta Y. The work done here is delta Y, then work done is the equation of work done is delta W is equals to P A delta Y or P delta V. Using the first law of thermodynamics from the path AC, we can write it as QP is equals to delta U plus delta W. In place of delta W, we can write P delta V. It becomes your equation number 5. By comparing equation number 4 and 5, we get the results NCP delta T equal to delta U plus P delta V. It becomes your equation number 6. Substituting the equation number 3, this equation, in equation number 6. Here we get NCP delta T is equal to NCV delta T plus P delta V. NCV delta T is adding this side, so on the other side it will be subtracted. So NCP delta T minus NCV delta T is equals to P delta V. This one is your equation number 7. Applying the equation of state to the process A, C. For the process A to C, we have two states. For state 1, PV1 equal to nRT1. For state 2, PV2 equal to nRT2. By subtracting PV2 minus PV1, it becomes nRT2 minus nRT1. By taking P as a common term, the rest of the terms become V2. We took P as a common term, so the remaining term is V2 minus V1 equal to nR, and on this side nr is taken as a common term. The rest of the term are 2 T2 minus T1. So it becomes P delta V equal to nr delta T, because it shows the change T2 minus T1. Here it shows the change in volume, so we take it as delta V. Here it shows the change of temperature, so we place delta T, and it becomes our equation number 8. Substituting equation 8 in equation number 7, it becomes NCP delta T minus NCV delta T equal to nR delta T. By taking n delta T as a common, rest of the term are Cp minus Cv equal to nR delta T. Common terms can be cancelled out. N delta T cancel, n delta T cancel. It becomes Cp minus Cv equal to R. Thus, the molar heat capacity at constant pressure is greater than the molar heat capacity at constant volume by an amount R, the universal gas constant. The second law of thermodynamics. The second law of thermodynamics gives more information about thermodynamic process. It states that heat cannot flow itself from colder body to a hotter one. The second law is also used to determine the theoretical limits for the performance of mostly used engineering systems like heat engines and heat pumps. If you want the transfer of heat from cold body to a hot one, we have to do some work. It can't be flow itself. Carnot engine. Carnot engine is an ideal heat engine free from all the dissipative effects and heat losses. It is free from all the losses. It is an ideal heat engine. It is reversible at every stage. The operating cycle of this engine is the Carnot cycle. The basics of the Carnot engine is the Carnot cycle, and to know about the Carnot cycle, have a look on this video.
Good day, ladies and gentlemen. Today's topic is the famous CARNOT cycle. So, what are the things that we need to know about this life-changing cycle? So, first, well, it is an ideal heat engine cycle by a French physicist, Sadi Carnot. It utilizes heat energy transferring from a heat source to a sink. In addition, it composed of four reversible processes. Reversible process means direction can be returned to its original position. Also, it uses ideal gas as its working medium. And no doubt this is a perfect engine. No friction between piston and cylinder walls, and no heat transfer between the surroundings and your system is considered. Now let's discuss how this interesting cycle works by exploring its processes, the four reversible processes. So now for the first process, process 1 to 2. This process is called isothermal expansion. Isothermal in thermodynamics means no change in temperature, or in other words, temperature is constant or not changing within this process. So what happens here is that the heat energy from the heat source is transferred into the ideal gas. As a result, the gas expands, which then increases the volume and decreasing the pressure. Now next, process 2 to 3, which is called an adiabatic expansion. Adiabatic in thermodynamics means that there is no heat transfer between surroundings and your system, or to put simply, all change in temperature is contained within a system, which as a result making the entropy zero. On this process, our volume increases and pressure decreases. Third process is the isothermal compression. So by compression, it means volume is decreased and as a result, pressure increases. On this process, heat energy from the gas is transferred into the heat sink. And finally, the last process. The last process is called the adiabatic compression. Since it's an adiabatic, all change in temperature is contained within a system, and our entropy is zero. Also, since this is compression, it means our volume decreases while our pressure increases. So that's it. That makes it a cycle. So now let me ask you this. Why Carnot cycle is the most efficient cycle? Mhm. Well, it's because Carnot cycle is a perfect engine. The processes are reversible, working medium is an ideal gas, and of course, the thermal capacity of heat source and heat sink is infinite, which makes no reduction to both during heat transfer, as we have observed, right? But for all those same reasons, it makes this cycle impossible to operate in our real world, as obviously those things don't exist. Well, of course, we should not forget that it contributed so much today. In fact, it is a model of our car engines like Otto and diesel cycle. And so that's it. Once again, this is Easy Engineering.
The last term is entropy. Mathematically, entropy can be represented as delta S equal to delta Q over delta T. Entropy is basically the disorder of a system. Entropy is the disorder. This applies only to the reversible path, even if the system actually follows an irreversible path. To calculate the entropy of an irreversible process model, it is a reversible process. When energy is absorbed, delta Q will be taken as positive and entropy will be increases. When entropy is expelled, delta Q will be negative and entropy will be decreases. So simply, what is entropy? Entropy is the disorder of the molecules, or simply the disorder. Thank you.